Hello everyone and welcome back to my online lecture. And today in our lecture we are going to talk about the queuing theory, especially queuing theory for data science part 1. And today I am going to give you some brief introduction to the queuing model, and later on we will see with some examples on how to solve some real-time problem using the queuing theory. Well, when you hear the word queuing or queue, what comes to your mind? Yes, you might think about the queue that you used to stand for buying the tickets, right? In the ticket counter. Probably it might be in the hospital, or it might be in the movie theaters, or it might be in the restaurants. There are different places, or library, or even bank. You may have to wait until your turn comes. Yes, there are a lot of places in which we see this queuing model. So as we see this queuing model, so we'll try to formulate some of the real world problems, and let's see how we can map it. Yes, as we have already mentioned, this is a class of model in which the customers arrive in some random manner. For example, if you consider a store, the customers going into the store is kind of random. Nobody knows how much customers comes into the store at any point of time. So we assume that the customer arrives in some random manner at the service facility. It can be anything. It can be a store, it can be a hospital, it can be a bank. Yes, it can be anything. So upon arrival, they are made to wait in a queue until it is their turn to be served in most cases. In a very rare case that as soon as the customer arrives in, he directly gets served if there is no other customers in the service facility. But generally speaking, he has to wait until his turn. So once served, they are generally assumed to be leaving the system. Yes, for example, like once the patient is serviced in the hospital, he generally leaves the hospital, or once a customer has been served in the bank, he leaves the bank, and so on. So for such models, we will be interested in determining among some qualities like average number of customers in the system or in the queue, average time a customer spends in the system or spends waiting in the queue. So when we say the system, it includes the entire facility. For example, if you are going to buy something in your grocery store, that grocery store is your system. So at any point of time, there may be more people in the system, but not everyone is waiting right there at the counter. Some are still buying some product, though they are soon to be waiting. So we can consider two cases. One is people, the list of people in the queue, and the list of people that been serviced right then at the service counter. So the average number of customers in the system includes the entire people inside the facility. The average number of customers in the queue means that those who are waiting to be served. And while these people are waiting to be served, there may be few of the customers are being served right there at that time. Well, we'll dig deep into it, and let's examine more on this model. So generally speaking, the queuing system consists of one or more queues and one or more servers, and operates under a set of procedures. So let's consider a reservation counter of an airline where customers from different parts of the world, country arrives and waits at the reservation counter. So you can take any examples. Depending on the served status, the incoming customers either wait at the queue or gets the turn. So if the system is free at the time of arrival of a customer, the customers can directly enter into the counter for getting service and then leave the system. Let's talk more about the whole thing. So here we say that there might be only one queue or maybe more queues. There might be only one service desk or counter, or there may be more. For example, sometimes when you go to some small grocery stores or small store, you might usually have only one cashier. So this one cashier point where you have to pay for what you have bought is considered as one service facility or one counter or one server. So in this process, over a period of time, the system may experience customers waiting and or server idle time. Yet we can see that server idle time, if there is no customers in the system, then probably the server is idle. For example, if there is no customer in the store, the cashier at the counter is kind of idle. So in any service or manufacturing system which involves this queuing model, the main objective is to design the system in such a manner that the average waiting time of the customer is minimized and the percentage utilization of the server is maintained above a desired value. So this is the main goal of the whole queuing model. I just repeat it. The main goal is we have to reduce the average waiting time of the customers. We don't want the customers to wait long time, and we want the server to be used or utilized to its full potential. So here are more examples or where we could find the queuing system. For example, the bank counter, toll gate, where we see the vehicles coming in as the members of the queue, and the toll collector is the server. In some cases, you have this electronic system which automatically connects to your device in your car, and a library where students are the members of the queue and the counter clerk is the server. Traffic signal, we have the vehicles as the member of the queue, and the signal point, or in other words the traffic signal itself, the signaling point is the server. Airport runway, planes and runways, maintenance shop, breakdown machines and mechanics. Yes, we can think more about it. There are a lot of other places where you find a similar example. So here is a basic model that you have in hand. So a single server queuing model. So you can represent this queue. For example, you have the number of passengers there and a server there. So it's kind of a single server system where you have only one queue. So there are a lot of applications to it. So for example, like if you visit this website, you will notice that it's a research article in which they have used the basic queuing model for scheduling the arriving passengers and serving the arriving patients. In fact, it's about the patients that are arriving in a hospital, where in fact they have series of single server where this patient has to pass. For example, initially the patient goes to the registration desk, spends some time there, and then he goes to the blood checkup or any lab checkups, and then he goes to the, say, some examination counters, then he goes to see the doctor, then he pays his bill. So there are different points where he has to wait in a single queue. Well, that has been kind of integrated research where you find the system can be used, but basically speaking, this is the model for single server queuing system. Here is the multi-server queuing model given to us. Yeah. So pictorial representation gives us more information. You can consider this like you have 4 server and then you have 4 queue, 1 for each server. It can be considered any of the example that we have seen earlier. For example, it can be a toll gate where the vehicles are moving in, and in each lane you have each toll collector. So the queue follows first in, first out model. Sometimes it's said as first come, first serve. Whoever comes first gets served. The first customer gets served. So when a first customer comes, he is the first person in the queue, and when the second person comes, he is added to the queue. You can see he has been added to the queue or enqueued. Then the third person comes in, he is also added to that queue, so he goes behind the second person. Then comes the fourth person, fourth customer, he is enqueued behind third customer, and so on. So as the 6 customers been enqueued, then if you want to dequeue it, or in other words, once the customer 1 is served, he comes out of the system, or he comes out of the queue, or he dequeued. After he is served, then comes the second customer, he is dequeued, and so on, one after another. So the first customer who comes in first gets served. That's why we call it as first come, first serve, or first come, first serve, or first in, first out. So that is a simple system that you have here. So the customer entering the system should form a queue, and if the server is free, they will get served right away. If the server is not free, they wait in the queue, then they get the service. But there are real time situations where there may be some variation in the system. For example, the number of queues may be more than 1. The number of server may be more than 1. So sometimes we do have some parallel counters, and moreover in real time we do have tendency to shift from one queue to another queue. So basically speaking, we are not considering that point today. We assume that the passenger, whoever goes into one queue, he stays in that queue until he is served. But if you like, you can model a system in which based on the availability of servers, the queues might be shifted. So these are some of the characteristics of this queuing process, and these are some of the important points that we have to understand, some of the basic 6 characteristics of the queue. We will see for the single server model, and later on we will take it over to multiple server models. The first point is the arrival pattern of customers. So, we want to know what is the arrival pattern of the customers as they come into the system. Then comes the service pattern of customers, how he has been served, and the queue discipline is we talked about the system in which first person whoever comes in gets served first. So, that is a kind of a discipline, first in first out. System capacity, so how much number of customers the system can handle. Number of service channels, how much service channel or server is there. Number of service stage, yes, at times you might have different stages of service. For example, as I mentioned earlier, a patient who is entering the hospital might go to different stages of service. First he might go to, say, the registration desk, and then he might go to some blood test, then he might go to some clinic. There may be different stages, right? Yeah. Let us see one by one, starting with arrival pattern of the customers. So, in usual queuing process of arrival is stochastic, and it is necessary to know the probability distribution describing the time between successive customers or inter arrival time. It basically means that when, let us say an example, in a store, the number of customer coming into the store, say for example, is like 5% per minute. So, this is the inter arrival rate of the customers. It is also necessary to know whether the customer can arrive simultaneously or like bulk arrival. So, anyway, we have to assume certain probability distribution method that could describe the arrival pattern of the customers. So, the assumption regarding the distribution of arrival rate has great effect on the actual mathematical model of the system. So, since the arrival rate in general is quite random, we are not sure like how the customer arrives, we are not sure how the vehicles arrive at the toll gate. Yeah, it is kind of a random, but the mean value of arrival rate can be expressed. So, here we are going to represent the mean arrival rate as lambda. We will consider the formula now later. So, basically speaking, this is the arrival pattern of customers. Then comes the service or departure pattern. As a customer enters into the facility, or if he enters into the store, he is being served. Say for example, the cashier is serving the customer, and the cashier has his capacity. For example, he might serve 10% per minute, that is the actual service rate, as the service pattern is the pattern in which the number of customers leave the system or departure that place. So, it also represents inter departure time. It is kind of a time period between two successive surveys. Yeah, this can be termed as a rate, because as I mentioned, it is per unit of time, like 10 customers per minute is an unit. Yeah, this rate assumes that the service channel to be always busy. We are not considering an idle time in this system. So, the assumption has been made as well. So, the assumption regarding the distribution of service is very important in forming this queuing model. So, generally speaking, this service pattern is exponentially distributed. So, the mean value of service rate or mean service rate can be represented as mu. We will see the formula later. Then comes the service channel. Yes, the customers may form the queue in the clinic, for example, and the queuing system may have single service channel. It can have multiple service channel. So, accordingly, your queuing model will be different. Yes, the number of service channel is essential part of modeling the system. So, this is a basic structure where we can see the entire population is there, and as they arrive into the queuing system, they fall into the queue first, and then they enter into the service area where it can be served by the server. So, in this example, you have multiple server, and once being served, the person can leave, the customers can depart from the queuing system. So, you can consider the entire system. Yes, for example, when I said the number of customers in the system, it includes both the number of customers who are waiting in the queue and the number of customers that are being currently served. But if I say the number of customers in the queue, it just represents those who are waiting in the queue. That's here. If I just say number of person in the queue, it includes just the queue part. But if I say the number of person in the system, it includes the whole system. Here comes the service discipline. As I already mentioned, we have first come first serve pattern. Yeah, so there is no other things, like everyone who comes first served first, whoever comes last will be served last. So, they have to wait in the queue unless there may be some discipline that you can establish. For example, there is this discipline, it is called the random and priority. So, in random pattern, the customers are chosen randomly from the queues. So, for some applications they are kind of randomly chosen, like as if your coach is picking up the team for a certain game, he picks up calling one guy after another who are in the queue, and comes the priority pattern. As priority patterns or other kind of service discipline, for example, when it comes to the vehicular context, the ambulance vehicle might get higher priority of service, or at times some vehicles like VIPs or VVIPs vehicles get higher priority in a system, they are getting served first. Or in other places, like for example, if you go to the airport or any other places, you always have a priority lane, like, or priority section, in which, for example, in the airport the crew members can go in for the checkup or a check-in, or the immigration check they can do in a priority queue, or even the elderly person can follow the priority queue, or the pregnant women and say disabled or person can also use the priority queues. Yes, in real time we do find such service discipline. then the maximum number of customers allowed in the system. So, the maximum number of customers in the system can be finite or infinite. In some facility, a limited number of customers are allowed in the system. Generally speaking, the number of customer in the system is infinite or infinity. For example, like the number of customers coming into a store, we are not, in fact, we are not limiting the number of customers coming into the store, and in fact, we don't know exactly how much number of customers would come, but basically speaking, we just leave it to infinity. So, calling source or population. So, the arrival pattern of customers depends on the source which generates them. For example, if there are only a few potential customers, the population is called finite. But if you have large number of potential customers, say over 50 or 60, we can call it as infinite. So, it is not an infinitely large numbers, we just say potential number of customers quite large. In that case, we can call it as infinite. So, yeah, the queue classification can also be performed with this particular queuing model system. So, we have A slash B slash C colon D slash E, where A means the probability law for arrival or inter-arrival time, and B means the probability law according to which the customer are being served. C is the number of service stations. D is the maximum number allowed in the system, in service and waiting, both, including both. Maximum number of customers allowed in the system. E is the queue discipline that it follows. So, we will examine a model today. Let us see, here is the basic notations that you have here. So, P sub n is the probability that the size of population at time t, and P sub O is this probability of a system being idle or free. Rho is the traffic intensity. L sub s is the average or mean number of customers in the system. L sub q is the average or mean number of customers in the queue. L sub w is the average or mean number of customers in the non-empty queues. W sub s is the average waiting time of a customer in the system. WQ is the average waiting time of the customers in the queue. We will see the formulas for this later on, but this is general notation. We will see for each queuing model the formula might vary. So, here is the model 1. The first model is called m slash m slash 1 colon infinity fi fo. So, this m slash m slash 1 represents the one server system which can have infinite number of customers in the system, and it follows the pattern of first in first out. So, this P 0, that's or the as we have just seen this one P naught, we can call P naught the probability of system being idle, equals 1 minus lambda by mu. Remember what is lambda? Yeah, lambda is the arrival rate and mu is the service rate. And generally speaking, this lambda by mu is also called the traffic intensity rho. And P sub n equals lambda by mu the whole power n times 1 minus lambda by mu. So this one LS, which is the average number of customers in the system, equals lambda by mu minus lambda. So this is the general formula. So here in today's lecture I am not going to derive these formulas. In fact, probabilistically you can derive each and every formula. We do have proof for all these formulas, but we are not proving it today. We will just see the formulas, and later on we will also consider various example on where we are going to use these formulas. So today's lecture we are just giving introduction to this queuing theory, where we can observe what these formulas are and what they represents. As the average number of customers in the system, so we mean the number of customers in the queue plus the person who is getting serviced. LQ is the average number of customers in the queue. So here we mean the number of customers in the queue excluding the person who is getting serviced. So this LQ equals lambda square by mu times mu minus lambda, and they can also be calculated as seen below here. So this LQ can also be represented as LS minus lambda by mu. So model 1 M1 M/M/1 colon infinity FIFO. So the one server model with infinite number of customers and first in first out service model or discipline. So we have these formulas. LW is mu by mu minus lambda, WS is 1 by mu minus lambda, WQ is lambda by mu times mu minus lambda. So we have this probability of n greater than k, where rho k for a queue and rho k plus 1 for a system, because it is a single server system in which only one server is there. So there is potentially one more customer is being served, excluding the number of customers in the queue. And we do have this exponential pattern for probability of WS greater than T. So there is a waiting time, they represented in e power mu minus lambda times T, and rho is lambda by mu. Okay. So here is a sample example you can look at. Let us consider a GS25 convenient store has one cashier at its counter. So 9 customers arrive on an average 5 minutes, while the cashier can serve 10 customers in 5 minutes. Assume Poisson distribution for arrival rate and exponential distribution for service rate. So you are asked to find the average number of customers in the system. Yes, the average number of customers in the system, which is LS, and then average number of customers in the queue or average queue length, which is LQ, average time a customer waits before being served, and the average time the customer spends in the system. Yes, so that's average time the customer has to wait and average time the customer spends in the system. So that's like WS and WQ. So we have all these formulas. You can write down these formulas and then you can execute it. So we will stop here and I will let you to solve this problem, and in our next lecture, which is continuation of what we have discussed today, we will see few more examples on using the formulas and solve some problems on queuing model where you have one server, and then later on we will see examples with multiple server. So until then, try to solve this problem. I will see you next time. Goodbye.